The next question on the energy work is from 2012, year 2012. Two small spheres A and B of mass m and 3m. A and B, I think this is not in. A and B of mass m and 3m respectively are suspended from a ceiling by means of strings of equal length. So this string and this string, they have equal length. That's something you have to note. Same length, right? Sphere A is drawn aside so that it is raised to a height h as shown and then released. Sphere A collides with sphere B, which is at rest, and they stick together. The maximum height to which the composite body swings is. Okay, interesting. Now let's analyze this step by step. Okay, let's analyze this step by step. I think we don't need to know the fact that they have equal length. I just wrote it so you know it as a fact. First, when you release the object, let's do it step by step. When you release the object, M initially will be at rest. Okay, and then it will eventually reach this point, and it will collide with B. It will collide with B like this. So when it collides with B, it will have a new velocity. When it collides with B, it will have a new velocity. Let's mark that velocity as maybe V1, something like that, V1. Right. And then this is M and this is 3M. Okay. And then they both are combining and moving together. So after the collision, I will use another color maybe. After the collision, now there is no, we don't consider them to be two different objects. You can take them as one single object of mass 4m now. Mass 4m now. Okay, you can consider them as one single object as a mass 4m. And with that velocity, now they will be moving now with a new velocity. I'll take it as V2. V2, right? Once they collide, they will be moving at velocity V2. And then the system now will go up and it will reach a new height. We don't know what that height is. We have to find that new height. And the new system now is 4m. Right, new system now is 4m. Right, just draw a random diagram here. The final final position is this. Let's take this whole mass as 4m. And remember, its final velocity will be 0. And the height from the center of gravity, well, let's take this as capital H, which we are supposed to find out in terms of simple H. So there are 3 steps. First, simple m moving from here to here, then both the objects combining, and then 4m going up. Okay, so let's start with, now there are 3 categories. I have used different colors, green, blue, and red. Let's start with the green part, right? Start with the green part here. What's happening? You can say A, B, and then we'll take this final position as C. Final position as C. No, A and B are spheres. No, never mind. So initially the green color part, what is happening? Simple M. So I can say kinetic energy. No, initially it has potential energy, no? Right? Initial potential energy, initial gravitational potential energy should be equal to final kinetic energy. If you take the bottommost level as the 0 potential level, you can say the gravitational potential energy is 0 at this level. Fine. So initial gravitational potential energy is going to be mgh. Final kinetic energy when simple m comes here, it's going to be half mv1 square. All right. So I have 2gh equals v1 square. That is the green color part. Right. Then they collide. And then they combine. They collide and combine. For that, we have to use momentum. All right. So final linear momentum in this direction should be equal to initial linear momentum in the same direction. What is the final linear momentum in that direction? That will be 4m, the total mass of both, into V2. And then it's equal to the other side, it's equal to m into V1. M into V1 was the initial momentum. Once they combine, it is 4m into V2. Right, so m and m cancels off. I'll be getting V2 is equal to V1 over 4. Okay, V1 over 4. Then, yeah, okay, V1 over 4. Then I think I'm here, I will have to apply energy. Therefore, we'll take V2 squared. What is going to be V2 squared? V1 squared over 16. And we know V1 squared, that is 2GH, 2GH by 16. So final answer for V2 squared is actually GH by 8. That is V2 squared. We will need that later. And the final part, for this particular part, what can we say? Now we are applying the equation for 4M object, the combined object. Initially, it has kinetic energy at the bottom, and then finally it will reach a gravitational potential energy, final gravitational potential energy. From here it goes up. What is initial kinetic energy? Half into mass into velocity squared equal final gravitational potential energy is mass into gravitational acceleration into the new height reached by the combined object. This is the equation. So as you can see, 4m and 4m can be cancelled out. And for V2 squared, we can substitute the value we have actually derived, and that is that would be how much? Half into GH by 8, and that is equal to G capital H. And from that, you will finally end up in capital H equal to how much? Simple H by 16, isn't it? Simple H by 16, because you can cancel out simple G from either side. Therefore, we will end up in that answer. So the answer for this question is first one. You have to consider that in 3 steps. In potential energy converting to kinetic energy, initial linear momentum equal to final linear momentum, initial kinetic energy equal to gravitational potential energy. So it's a process. All right. And the other thing, sometimes some of you might be tempted to do the question like this. Initially, the object has mgh energy. Finally, the object has 4m into g capital H energy. You can't equate those two potential energies. If you do that, it's wrong. The reason is there will be an energy loss due to this collision and combination. I hope you understood that. But total gravitational potential energy at this point and total gravitational potential energy at this point, they are not equal, because in the middle there will be some energy loss. So you have to be careful. You have to consider this way. The next question under energy and work, it comes from 2013. If the mean output pressure, so they're talking about pressure, mean output pressure is output pressure of the heat is 1.2 into 10 to the power 4 Pascal, and the mean blood flow rate is 5 into 10 to the power minus 3 meter cube per minute. The mean output of the heat is. And look at the answers. All the answers are in watt. So by mean output, they mean what is the output power, because answers are in watt. And the interesting part is they have given us pressure. So pressure is given to us, that is 1.2 into 10 to the power 4 Pascal. And they have given us blood flow rate. It's in fact volume flow rate. Because look at the unit they have given. 5 into 10 to the power minus 3 meter cube per minute. So you can convert it to meter cube per second. How do you do that? 5 into 10 to the power minus 3 divided by 6. If not, that can be written like this, no, people? Meter cube in 1 minute. So you can write it like this. 5 into 10 to the power minus 3 meter cube in 60 seconds. Meter cube per second. So that, right, fine. So finally, I'll just leave it like this without simplifying. Minus 3 over 60 meter cube per second. That is the volume flow rate. But since you are in grade 12, you haven't studied an equation connecting pressure and volume flow rate. But you know the equation for work. So let me derive an equation very quickly. Now we have learned power, that is equal to work over time. You have studied in O-level. And what is work? That is force into distance divided by time. Force into distance divided by time. Now, when you see force, you should be able to find a relationship between force and pressure. We know pressure is equal to what? Force divided by area. Therefore, you can say force is equal to pressure multiplied by area. Instead of force, we can substitute that. Pressure multiplied by area. So I'll substitute it here. Still we are dealing with power. Power is equal to, for force, I'll put pressure multiplied by area multiplied by distance divided by time. Okay, now what is area? By area, I mean cross-section area. Okay, what is cross-section area multiplied by distance? What is cross-section area multiplied by distance? This whole thing can be considered as one single thing, correct? This whole thing. What is that? It is in fact volume. Pressure. I'll write pressure first of all. Pressure, and then multiplication. This whole thing is actually volume. And volume, and you have to divide by time. Instead of dividing both by time, I will divide this by time because it's multiplication. I can write like this, or put time below both also. Same. When you divide volume by time, what do you get, people? When you divide volume by time, you get volume flow rate. So it is pressure into volume flow rate. Even if you haven't studied an equation, you could figure this out. Let's finish it off then. Power is equal to, what is the pressure now? 1.2 into 10 to the power 4 multiplied by volume flow rate, that is 5 into 10 to the power minus 3 divided by 60. I think the answer is 1 watt, because on top we will be getting 60. 1.2 into 5 is 6. 10 to the power 4 into 10 to the power minus 3 is 10. 6 into 10 is 60. 60 over 60 is 1. 1 watt is the answer, and that should be the second answer. Well, the next question is from 2013. A body of mass 2m shown in the figure is placed on a smooth horizontal surface, and a small block B of mass capital M is placed at the top of the body. Right, it's like a wedge, okay, which is smooth. Starting from rest, block B slides down on the smooth surface A. At the instant when block B leaves A, the speed of A is given by, okay. Now, the top of the body, starting from rest, block B slides down on the smooth surface A. Okay. At the instant when block B leaves A, the speed V of A is given by. Okay, fine. So we need to find the speed of A. Now I think this, yeah, fine. Now let's do it like this. I'll cancel this out. This is how they are initially. This is how they are initially. Initially, velocity of B is 0. Velocity of B is 0 initially, right? And when you allow B to slip downwards, so there is suddenly, now this is a smooth surface, and people, the bottom surface is smooth. Now the initial momentum is 0. Therefore, when you allow B to slip down suddenly, we are creating a momentum suddenly to the right direction. But total momentum must be 0 now. Therefore, to compensate for that, A, which is on a smooth surface, which will start moving to the left. Okay, so you have to consider a situation like this. This is just before when the object was released from that. Now let's see what happens when B actually leaves A. Then I have to redraw the diagram, and it will look like this. Now see, right? A also will have a speed. I'll take that. That is the speed we have to find out. VA. That is what we have to find out. And B will have a speed as it leaves, like this. Right. Two unknowns are there, unfortunately. One is the speed of A. The other one is speed of B. This is mass is capital M, mass is 2. If there are two unknowns, we need two equations. We can't do this with just one equation. Okay, right. So let's start. You can apply energy as well as momentum. Energy and momentum. Okay. So first of all, if you talk about momentum, final linear momentum, it should be equal to initial linear momentum. I am applying this for the system. I'm applying this for the system. So when you take the system, we have to choose a direction. I'll choose it to the left side. Never mind. Final linear momentum in the system is how much? 2mva minus mvb, because the directions are different, so minus sign comes. But initial linear momentum, this is when b was just released, it is 0. Nothing is moving initially. Everything was at rest initially. Therefore, I can say 2 MVA, that is equal to MVB. M and M can be cancelled out. 2 MVA, it's equal to VB. Now, VB is not our concern. We need to find out VA, not VB. We need to find out VA. Right. Now, for the entire system, let's consider energy. Energy. All right. So, talking about energy, potential energy of B has reduced. Potential energy of B has reduced. Potential energy of A, it doesn't change because A is moving horizontally. Its potential energy can't change. All right, but B's potential energy has changed, and that initial potential energy of B is the only energy left in the system if you take this as your zero potential level. Hope you can understand. Initially, both 2M and M are not moving, they are at rest. But M, capital M, is at an elevation. So I can say, yeah, that's the initial part. And finally, M is at its same, 2M is at its same level. So there we don't have to consider its potential energy. M has come down and it has a kinetic energy. 2M also has a kinetic energy. So the equation should be final kinetic energy of A plus final kinetic energy of B. So those are the energies left in the system at this point. Initially, there's only one energy in the system, that is gravitational potential energy of B. You have to apply to the whole system. Right. Now, what is the final kinetic energy of A? That's going to be half into 2m into VA squared plus final kinetic energy of B, that is half into m into VB squared. And the initial gravitational potential energy of B, what is that? That is going to be mgh. Fine. So we can cancel out capital M from all these expressions. And I have to do one more thing. We need to find out VA, people. Speed of B, speed of A actually. Speed of A. So it's VA squared by 2. I don't want VB in my equation. So I'm going to get rid of that. And how do I do that? This is plus half into VB squared. It's going to be this. Now, if VB is equal to 2VA, what is VB squared? Okay, wait, what is VB squared then, people? VB squared is going to be 4VA squared. Both must be squared. So 4VA squared, that is equal to GH. That is equal to GH. I think I made a mistake here. M and M should, sorry, 2 and 2 should also be cancelled out, people. 2 and 2 should also be cancelled. Therefore, this half won't be there. Extremely sorry about that. Right. It's actually VA squared plus. And what do we have here? What do we have here finally? This is VA squared plus 2V squared, that is 3VA squared. Right? 4 and 2 divide 2. VA squared plus 2VA squared, 3VA squared, that is equal to GH. And finally, VA squared is equal to GH by 3. And finally, VA is going to be equal to square root of GH by 3. And that is fourth answer. Okay, the next question is from 2016 under energy. Let's see what this question is all about. An elevator of weight 5000 Newton carries a load of 5000 Newton. While moving vertically upwards in a building, it travels at a constant velocity from second floor to 12th floor in 20 seconds. All right, a lot of things are happening. So why don't we just try to put this into a diagram? It's moving vertically upwards. Is it? Yeah, it's moving vertically upwards. So this is the elevator. It has actually moved vertically upwards from second floor to 12th floor. The height of each floor is 4 meters. That means the elevator has moved a total distance of how many meters, people? From bottom to bottom, if you consider 40 meters. Is it? This is 40 meters. And how did I get that 40? That is 4 into 10. Each floor 4 meters, 10 floors 40 meters. And total weight of the elevator must be considered, that is 10,000 Newton. Okay, that means what is the mass? 1000 kilogram. something like that. Total mass inside the elevator is 1000 kilo. But the most important thing is the elevator is moving at a constant velocity of, it's not mentioned, it's moving at a constant velocity. So there is no change in its kinetic energy. If I take the time at this point as 0, and it takes time, how many seconds? Time 20 seconds, is it? Yeah, 20 seconds to move from there. 20 seconds. So this is 20 seconds. Okay. If only 80% of the power generated by the motor is consumed to lift the elevator and the load against gravity while moving at constant velocity, the power of the motor is right. Okay. So let's first of all find out now what has happened to the elevator. Its energy has increased. Let's consider this as our zero potential level. Therefore, at this point, we can consider that the gravitational potential energy of the elevator is 0. Now, there are two instances. I'll take this position as A and this position as B. So you can see at A, it's like it has kinetic energy and potential energy. At B, it has same kinetic energy, but the potential energy has increased. Kinetic energy has not changed, so we don't have to worry about its velocity because it's moving at constant velocity. So this question I'll approach in a little different way. I'll say increase in potential energy. Increase in potential energy. Because we have to find the power. Okay, increase in potential energy is equal to mgh. What is the mass? That is 1000. What is g? That is 10. Into height traveled by the elevator is 40. Yeah, and that will be, how much is that? That is going to be 400,000, is it? Joules. 1, 2, 3, 4, 5. 5 zeros. 400,000 joules. That is increase in potential energy. So, power consumed by elevator. Power consumed by elevator. Power consumed by elevator is equal to, what is the equation for power, people? Change in energy divided by time. Change in, okay, gravitational potential energy, you have to divide it by time. So the change in potential energy is 400,000 joules. The time taken is 20. Therefore, it's going to be 20,000 watt or 20 kilowatt. Now that answer is there, but that's not the correct answer because they are asking for the power of the motor. The power of the motor, right? Then there is something called efficiency. That efficiency is given by this equation. Efficiency is equal to power consumed by elevator, that is the desired power, divided by power input of motor. I mean, output divided by input. When you divide the desired output power by total input power and multiply that by 100, that will give you the efficiency. In this question, they have given it as 80%. If only 80% of power generated by the motor is consumed. So this is it. So what is the power consumed by the elevator? That is, I'll write it again here. That is 20 kilowatt divided by power of the motor. So I'll say power of the motor, and that is equal into 100 is equal to 80. Okay, so if you simplify this, people, power of motor, you will be getting 25 kilowatt. You can simplify it. This goes up, 80 comes down. When you multiply everything, you'll end up in 25 kilowatt. So the correct answer for this question is second one. It's basic equations, O-level equations, efficiency, power, and everything, potential energy, right? So no need to panic. It's just you have to visualize this and get the answer. Next question is from A-level 2017. Question from the 2017 paper, and let's see what it says. A monkey climbed a certain vertical height along a vertical rope with uniform speed in 30 seconds. Right. Later, the same monkey climbed the same vertical height along a spiral path of 75-meter path length with another uniform speed. Right. If the monkey applied the same power throughout its motion in both cases, the speed with which the monkey has climbed the spiral path is. Okay, now that's pretty interesting. Let's see. Okay. Now, first of all, in both the situations, the monkey was at the ground initially. The monkey, I'll just draw a circle. Monkey was at the ground, and finally, the monkey has reached this point, the ceiling or whatever. So, for both situations, remember what is equal. For both situations, uh, gain in potential energy is equal. Hope you can understand that. Gain in potential energy is equal to, right? Because mgh, constant velocity. No? If it, let's say it starts at V1, it reaches at V1. No change in kinetic energy. It starts at V2, it finishes at V2. No change in kinetic energy. So the only change is the change in potential energy, and that is equal for the monkey because h is same. Height we have to consider, not the path. We don't care about the path. We don't care about the path. We care about only the height. Okay, so we know power is equal to uh, gain in gravitational potential energy divided by time. If gain in potential energy is equal, what can I say? Gain in gravitational potential energy and power both are equal, constant. So time should also be constant for both the monkeys. Time should be constant for both the monkeys. All right. So that is the conclusion you can get from this.